I think I hit the wrong button. All right, here we go, class. So complex one. Complex number operation. So I'm going to talk to you about a new number set, new way of doing addition, new way of doing multiplication, division, all kinds of stuff, but don't worry, it's a lot like old stuff that you've seen before as well. Believe it or not though, in order for us to kind of jump into complex numbers, we need to visit an old, I don't know if I'd say friend, and it's definitely not a friend, it's maybe some of you might be an enemy, that's long division. I know, but I'll try to make it short. So, just as a review, there's kind of, and it's only not even long division, okay? It's just division by 4. That's not too bad. When you would do like 12 divided by 4, anybody remember what that is? I know it's been a while. And you look, use decimals if you need to. 3, that's right, okay? Because you do 3, and then you do the 3 times the 4, and you'd have the 12. Remember that whole thing? And then 12 minus 12. Wow. Okay, yeah, I know. We're way back machine here. And sometimes we would then say remainder 0, although if there was 0, we never really kind of did that, right? But what if it was 13? What if it was 13 divided by 4? 3 remainder 1. You remember your remainder division. See, it's 3, and then you put 12 there, and 1. So you'd say 3 remainder 1. Sort of like that percent thing, right? Right? What about 14? 14 divided by 4. Don't just go with the pattern. Think it through. 14 minus 12 is 2. So it's 3 remainder 2. I think I'm seeing a pattern here. What about 15 divided by 4? Go ahead, you can shout it out now. 3 remainder 3, right? Now, someone new here, 16 divided by 4 is going to be 4. I thought I was going to have y'all. I thought it was going to be like, that's it. So, yeah, it's 4 remainder 0. So talk to me about the remainders. Okay, can't have a remainder bigger than the actual divisor. Yep. And it cycles around. We're going to see that as it relates specifically to imaginary numbers. And then we'll see that imaginary numbers relate to complex numbers. And that'll be great. So do y'all remember imaginary numbers? Yeah. From Algebra 2? It's kind of such a weird term. Imaginary numbers. Alright? I mean, I guess you could say there's one imaginary number. Anybody know what that imaginary number is? It's I. I'll say imaginary number. Imaginary number I. I kind of try to do a little kind of cursively. And still doing pop quiz. What if you stop answering questions here, Robert? Okay. It equals the square root of -1. We use that for different things. We deal with quadratics and stuff like that. Okay. Technically, you can't have square roots of negative numbers because square root is asking the question, what number times itself equals this number? And there's no number that when you multiply it by itself, you get a negative number. Because if you have a negative number and a negative number, if you have a negative multiplied by itself, it's going to be positive. If you have a positive multiplied by itself, then it's going to be positive. So it doesn't really make sense, you know, what number multiplied by itself is going to equal a negative number. But we decided, well, we'll pretend that there's a number. It's the imaginary. And we'll say that's I. So, in other words, I squared, I times I would equal -1. Now, it's no use thinking, what is I? Because it's not a real number. It's an imaginary number. Now, if you're a realist, I think, Dominic, you're very realistic, very pragmatic. How is this gonna, what does this mean to me? Your cell phone would not work without the mathematics of imaginary numbers. Anything dealing with electronics uses what we're about to kind of start going through here. Now, I'm not going to take you on starting with I and ending with complex electronics, but I will tell you this is the the foundation of that pathway, as well as some mechanical engineering and probably other disciplines that I'm not as familiar with. All right? So I is equal to square root of negative 1. I squared is equal to negative. So what about I cubed? What would that be? That would be square root of negative 1 times the square root of negative 1 times the square root of negative 1. This times this is negative 1, so square root of negative 1 times square root of negative 1 is negative 1. And then times the square root of negative 1. So it's negative 1 times square root of negative 1. Now, what is the square root of negative 1? It's I. So I cubed is negative I. Mr. York may have gone through this route, I don't know. I to the fourth would be square root of negative 1 times square root of negative 1 times square root of negative 1 times square root of negative 1. So square root of negative 1 times, that's I squared. So it's sort of like it's I squared times I squared. We saw earlier that I squared is negative 1. So what's negative 1 times negative 1? 1. But what about I to the fourth? I to the fifth. Sorry. All right, wait a minute. I to the fifth. I'm going to make it easy for us. That's going to be I to the fourth times I. Well, Rory, what was I to the fourth? 1. So 1 times I. So on I to the fifth, we are back to just I. Kind of loop back around. What about I to the sixth? That's the same thing as I to the fourth times I squared. Right? I to the fourth is equal to 1. So 1 times I squared. We look back up here, I squared was negative 1. And hopefully you can see, if you want to, we can continue doing this example a few more times if you want, but as honor students, I think you can kind of see the pattern. We are going to follow this pattern, square root of negative 1, or negative 1, negative I, 1. Square root of negative 1, negative 1, negative I. So, I to the first, I to the second, I to the third, I to the fourth, I to the fifth. And it loops around every 4 times. So we saw at the I to the fourth, it was equal to 1. We can see again, going on down the line, I to the eighth. That would be I to the fourth times I to the fourth. So 1 times 1, so that's 1. Somebody here front row, tell me, what would be another power of I that would also give us 1? And don't tell me 12. 16. Okay, 16. How did you get that? You divide by 4. So we got multiples of 4 right here. Somebody on back row, not Robert. Give me another number right here, power of I, that would give me 1. 20. Okay, I think we're pretty good. So if you know your powers of I, or your powers of 4, then you can pretty quickly tell whether or not it's going to be 1 or not. And then what these guys are would correspond to the remainders. Okay? So think about it with me for a second. So if we think I to the 21st, okay? Well, if you do 21 divided by 4, we know that's 5 remainder 1. This is 1 past the multiple of 4. Namely, it's 1 past 20. So therefore, this is going to correspond to the I to the first. So we could say it's equal to square root of 1, or just it's equal to I. If we were at 22, so I to the 22, that's remainder 2, that's 2 away from the nearest multiple of 4, so that would correspond to equal the same as I to the second, so that's going to equal negative 1. So if we just kind of have this pattern, we just recall follow this pattern, I'll kind of erase these middle parts. This is what we need to think. It goes, in fact, we normally just say, I, negative 1, negative I, 1. It's going to follow that pattern. So because of that, we can very quickly figure out things like what is I to the 35th? So you think, what's the nearest multiple of 4 that's lower than 35?
32.
Probably I to the 32. That's the nearest multiple. Okay. And then so this would be I to the 32 times I to the third. So I need 3. So it's 3 more past that. So 1, 2, 3. This is going to equal negative I. I to the 100. Now let's see. The question is, what's the nearest multiple of 4 that's going to go into 100?
50. 20. No.
Keep going. 25. Like I goes into like 4 times 25 is going to give us 100. So 100 is actually a multiple of 4. So that's just multiple of 4. We're putting it there at 1.
Wow.
But if it was I to the 103, we're 3 away from that multiple. So now you're looking at the negative I. This is kind of making sense a little bit? Okay. What about negative numbers?
Oops.
Let's deal with that for a second. So I to the 0
1.
is what anything is to the 0. It's 1. I to the negative 1 is 1 over I. Now what you need to think about that is that's 1 over the square root of negative 1. And historically, for good reason, we'd all like square roots of the denominator. So let's multiply this by square root of negative 1 over the square root of negative 1. So we have square root of negative 1 over, square root of negative 1 over negative 1. And so this looks like it would be square root of negative 1 is I, and divided by negative 1, so we've got negative I. Seems pretty good. I'm guessing it's just the opposite direction. Perhaps, because it looks kind of like we've got 1, negative I. Let's go 1 over I squared. I squared, we saw earlier, was negative 1. So we're negative 1. That's negative 1. I to the negative 3 is 1 over I cubed. I cubed was negative I, so 1 over negative I. We'll think of that 1 over negative the square root of negative 1. We still want to rationalize the denominator. We'll kind of deal with that. So that's going to be square root of negative 1, square root of negative 1. So that's going to be square root of negative 1 over negative 1 from this right here. And then square root of negative 1 times square root of negative 1 is going to be negative 1. So that's just going to be I. Negative times negative cancels that. And I to the negative 4th. 1 over I to the 4th. So 1. And then it's going to repeat. Negative I, negative 1, I, and then 1. So every 4 that we go down, it's going to be 1. Alright, so when we're multiples of 4 in the negative, we're here. And then if we're, so for instance, I to the negative 16 is going to be 1. I to the negative 24, that's a multiple of 4, that's going to be 1. But then the next one after that, I to the negative 17, it's sort of like we wrap back up here, that's going to be negative I to the negative 25th. Okay, so that's wrapped around, that's going to be negative I. So what's interesting is, what is I to the positive 17? I wonder, anybody know? I to the positive 17. 17 is one past. So yes, that's going to be I. What's I to the positive 25? Well, that's going to be positive I. It's just, I wonder if this is just like if it's negative, the opposite. You see, like, let's think about what's I to the 18. That's 2 past, so that's going to be negative 1. I to the negative 18 would be run back here. Yeah, it's not. That's a nice. That would be nice if it worked out. Okay, but do you see the pattern? Okay, it seems like though this is such an easy pattern, like we could program it. Let's see if our calculator can help us solve this thing here. Is there an I button on your calculator?
Yes.
There's the alphanumeric I, like if you're spelling out your name, but second period I think has the little cursive I. Yeah, that's what we want, second period. So I don't know, try this one. Try a little cursive I to the 35th power. And let's see if it gives us negative. Oh, what did it say here? What did it say? 5e negative 13 minus I. Okay. Does anybody know what 5e to negative 13 is? 5 times 7 negative 13. Okay, so minus I. So 5 times 7 negative 13, that means 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's a decimal point. 0.000000000000005. 5e negative 13 minus 9. For all practical purposes, what is 5e to the negative 13? It's that, which would essentially be approximately 0. Would you all agree with that? So when I see 5e negative 13, or anything that's e negative 10 or something like that, what's going on is your calculator's doing some approximations in this multiplying stuff like that using some other techniques, which I can show you later if you're curious. But it's doing some approximations, and it should be getting 0, but because of rounding issues and because of the memory limitations of your calculator, it's not going to get exactly 0. This really should be 0, okay? If you can interpret that properly, then you'll realize that this is really 0 minus I, which is negative I. Guess what the correct answer is? Negative I. So you can use your calculator to use this, but to solve these problems, but you have to know how to interpret some of this stuff, and essentially know what to throw out and legitimately how. Let's do another one, maybe a little bit easier one. What's I to the 8th on the calculator? Call it out there for me, Grace. Minus 2e to negative 13i. Okay? So, I'll write that over here. So, that's 1 minus 0.0000000, whatever, a bunch of zeros, 2 times I. Well, that 0.000, alright, once again, essentially 0. So we have 1 minus 0. What is 1 minus 0? 1. What did we say that I to the 8th was based on our knowledge. 1, okay? One more. Let's try I to the negative 17. Now, what are we expecting, class? I to the negative 17. We're expecting negative I. What does the calculator tell us? I to the negative 17. Naomi, what do you get for I to the negative 17? I'll say it again.
3e -13
Minus I. Everybody else got something like that? 3 to the negative 13, I think we can all say, calculate approximations, that's essentially 0. So 0 minus I, and 0 minus I is just a negative I, which is what we were expecting. So can you use the calculator to sort of solve out these problems? Yes. You gotta be a little bit, you gotta know how to use the calculator. You gotta be smart about it, okay? But there you go. So now you know the pattern. These sort of problems right here, this 3e, this number plus and minus and I is actually the next thing that we're going to talk about. So, for me, it's turn my paper over. For you, it might be something else. That's imaginary numbers. Let's expand that idea a little bit. So imaginary numbers, we've got I. What about 5i? Is that an imaginary number? That's it. It would be. It's 5 times I. What about negative 42i? Just take negative 42 times I. It's imaginary. We could have 3.14i. Okay? All of those make up what we call imaginary numbers. Now, does anybody know what the opposite of imaginary is?
Real numbers.
I haven't heard complex, nope.
Real numbers.
Real numbers, right? Just like in story time, right? The opposite of imaginary is real. And you've heard that word a lot of times, like, well, the answer is all real numbers. Okay, well, this is the context for that sentence. Some real numbers are numbers like 17, 99, 2.121212 repeated, 3.3 repeated. Numbers that don't repeat but still go on forever. Like 3.14159, like pi, that's a real number. It's not rational, but it's still a real number. There are different groups within the real numbers that I know in your previous math classes you talked about, like whole numbers and natural numbers and integers and like rational and irrational and yada yada yada. But that is what we call, oh, I need to put negative number, negative 7. Those are real numbers. Both of those are actually part of a bigger universe called complex numbers. Complex numbers, there you go. That's everything. You have some that are, technically this would just be the pure real numbers. These would be pure imaginary numbers. But like any Venn diagram, you have some stuff that's in the box that's not inside the circles. And those are what we call complex numbers. Numbers that have both a real part and an imaginary part. I probably should have made that, I can make that an intersection. I don't know what. There we go. 3 plus 2i. Seven minus 40i. numbers that have both a real part and a complex part. Or imaginary part, yeah. And so we call those complex numbers. So allow me to tell you the rectangular form of a complex number. This is the general form. A plus BI, where A is the real part and B is the imaginary part. So A is like you and B is like your friend.
Dang it.
Alright? No. She goes to another school. She goes to another school, Too close to home there. Alright, so examples. 2 plus 3i. 17 minus 4i. 1.123 plus 9.214i. Or even 1.37 times 10 to the 9th minus 4.18 times 10 to the 50th I. We could write that also as, you could say 7e9 plus 12e negative 2i. Well, remember the e stands for the times 10 to the whatever. This would be 7 times 10 to the 9th plus 12 times 10 to the negative 2nd I. Those two numbers are the same, but I'm going to keep using that capital letter E sometimes just so you're not so weirded out by it when you see it on the calculator.
So is E an imaginary number?
This right here, E, is a placeholder for times 10 to the power.
I know, but like.
But now you're talking about lowercase e. Perhaps, maybe?
No.
Talking about that E?
Yes. I was just asking.
No. That E is because mathematicians got lazy and they don't always want to write times 10 and then put this number as the subscript. And so they put E right there, and you're like, what do I really need to know? I need to know the 7, I need to know the 9, and give me some sort of single letter notation to get that across.
Okay.
So that's what E, that's what capital E means in that situation. But there is actually the lowercase letter e that I get real excited about, because that's Euler's number, and that's used like all over the place, and is probably as important, maybe more important than pi. E pi I 0 negative 1. This is awesome stuff. These main concepts are like civilization changing. You gotta take my word for that. Maybe sometimes we'll have a math history thing, but I don't know. There's like, for some people, it's like the two most important things combined, But anyway, I think it's kind of fun. But those are some neat things. We'll talk later about E after spring break, lowercase e, after spring break. Yeah, that's not related to it, but that was the I sum pi. I used to do the sigma. That's the one I think you're thinking of. Okay, now I've just told you about a whole new set of numbers. All right, we're gonna start over from scratch now. When you first started learning about numbers, what are some of the things that you did with numbers. You added them, and then you subtracted them, and then you multiplied them and divided them. So what we're going to do is we're going to learn how to add complex numbers, and how to subtract complex numbers, and how to multiply complex numbers, and how to divide complex numbers. Do all those fun things that you've already done with real numbers. Now we're going to be able to do those same operations with complex numbers. Okay? So don't worry, it'll be a lot faster to learn all your adding here. So let's talk about adding complex numbers. So 5 minus 3i, that's one complex number, plus negative 2 plus 4i. In dealing with complex numbers, you kind of have to get over the fact that there's actually multiple numbers in what I'm calling, like multiple symbols here, in what I'm calling a single number, okay? You just gotta like deal with that abstract concept. This is a number, and this is a number, and we're adding them together, okay? Don't think of them like two objects. And you can actually use some object programming classes and stuff like that as a good way of having instance variable for the real part and for the imaginary part. Y'all take my computer programming classes next year, you'll know what I'm talking about. Now, good news for you, Dominic. Don't put that calculator down. All right, we'll get to that good news here in a little bit. All right, but the good news about adding complex numbers is we can actually treat this like an algebraic expression. Okay, where we combine like terms. Okay, so we can actually treat this almost like that's a, 5 minus 3x and negative 2 plus 4x. Like we can actually treat that x. In other words, combine like terms, which in this case is the real parts. So 5 plus a negative 2, so the same thing as saying 5 minus 2, so that would be 3. And then the imaginary parts, negative 3 plus 4i is 1i, so I can put plus 1i, the cyclops, yeah, or I could just say plus I. 3 plus I, there you go, that's it. That's how you add complex numbers. Add the real parts, or combine the real parts and combine the imaginary parts. I also say, or subtract, I've got an example here. 10 minus 2i minus 14 minus 6i. I have a complex number minus another complex number. You can literally just think of it as like that minus is getting distributed here, and you can say 10 minus the 14, negative 4, and then the negative 2 minus a negative 6. Well, minus a negative, the same thing as adding, right? So negative 2 plus 6i. I think that's positive 4. That's not really a very helpful example. We'd better have two different values there, but that's okay. That's the answer. Complex number minus complex number equals complex number. All right. Let's do some multiplication. We're gonna learn a whole new way of dealing with two set of numbers. So do one of my favorites here. 2 minus 3i times 7 minus 4i. And good news, once again, we can just treat this as algebraic expression, okay? And there was a process. Does anybody remember the name of that process when you were multiplying two binomials?
FOIL.
FOIL, yeah, okay, so the first. So the 2 times the 7 is 14. Sometimes you can also think of it as double distribution. 2 times the negative 4i is going to be a negative 8i. The negative 3i times the 7 is a minus 21i. And the negative 3i times the negative 4i is a negative times a negative, so that's going to be a positive. 3 times 4 is 12. And I times I is I squared. And we'll do some combining of like terms. So we have 14 minus 8i minus 21i gonna give us negative 29i. Now, look back in your earlier notes, what is I squared? I squared is negative 1. So I could really write this as minus 12, because it's equivalent to negative 1. But wait a second, I can combine this again. So 14 and the minus 12 is going to give me 2. So 2 minus 29i. Alright, hooray! So if you can combine like terms, and if you can FOIL on combine like terms, then good news, you can add, subtract, or multiply complex numbers. Ooh, we got lots of time. What about divide?
I didn't say that.
Well, not so much. It's a little annoying.
Easy. Don't you go to multiply by the conjugate or something?
What does that mean?
What do you say? What do you say?
Oh, good. This is our last for the end. Here we go. 5 minus 3i divided by 1 minus 2i. Well, when you did polynomial stuff, when you were doing division, you kind of would do factoring, or you might do like that synthetic division, if you ever mess with that. With complex numbers, our analogy here sort of breaks down. It's helpful for you to remember, what is that? That I is actually a square root. So what we need to do is, when we're really not going to effectively do a lot of division or whatever, we're just going to do a simplification. So you need to think, all right, this actually has a square root in the denominator. So just like earlier, remember we had the square root in the denominator, we multiplied by square root of negative 1 or square root of negative 1. We multiplied by that thing to get rid of it. We are going to, the way we solve this is we're going to take that whole thing and multiply it. So for your notes, you might want to do this, otherwise it would be kind of confusing about what we just did. We're going to multiply this by the conjugate of the denominator over itself. So 1 plus 2i over 1 plus 2i. Not conjugal, conjugate.
It's the conjugation.
That's when you manipulate the verb.
Yeah.
So, what we're doing here, so we are multiplying by the conjugate of the denominator over itself. The conjugate is the same number, but with the opposite sign, S-I-G-N, in between the real part and the imaginary part. So the conjugate of 1 minus 2i is 1 plus 2i. The reason that we do this is because now we can treat that top part like a FOIL problem. 5 times 1 is 5. 5 times 2i is 10i. Negative 3i times 1 is negative 3i. Negative 3i times 2i is a negative 6i squared. Denominator, 1 times 1 is 1. 1 times 2i is 2i. Negative 2i times 1 is negative 2i. And a negative 2i times a positive 2i is a negative 4i squared. Let's do a little simplification here. 5, 10i minus 3i, so that's going to be 7i. The minus 6i squared, if you remember, I squared was what? It was negative 1, so this is going to be turned into a plus 6. 1, now this is fun, plus 2i minus 2i, those cancel out to 0. And then I have minus 4i squared. Well, the I squared is negative 1, so negative 4 times negative 1 is going to be a plus 4. So now I'm going to have 5 plus a 6, so that's 11 plus 7i all over 5. We can split that up, split that fraction up to say 11 over 5 plus 7 over 5 times I.
Wow.
How about that, huh?
No,
Oh, I know, that's awesome, great. What is 11 over 5?
1.2. Or no, 2.2, sorry.
2.2 plus 7 over 5. That's 4 I. So it's multiplying by, multiplying by conjugates, adding, subtracting, all that stuff like that. Now, you're not always going to have a TI calculator at your fingertips, but if you did, let's try typing that into the calculator. 5 minus 3i, put it in parentheses, plus negative 2 plus 4i. Yeah. And you gotta ruin my punchline here. But I don't know if Desmos can do that. So, my 30-second journey into Desmos trying to deal with imaginary numbers did not do it. It does help you graph imaginary numbers, which is what we'll talk about tomorrow. But simplifying complex operations, no. Anybody have any luck when you add 5 minus 3i and negative 2 plus 4i? You get 3 plus I? What about, this is one we really care about, what about this one? 5 minus 3i, all of it in parentheses, divided by 1 minus 2i. Show me that on the calculator as I walk around. Hopefully, if it works, you're going to get 2.2 plus 1.4. And if you turn math enter, it might be right?
Are you serious?
Try math enter in. Hey, look at that. It even does the...
You put a negative sign on a minus sign.
Same thing. That needs to be a minus, but you hit the negative button.
No, wait, I
Great, so now all you need to do is buy a TI calculator and you can solve your homework.
I'm doing the minus.
I already have.
That looks good.
It's called minus brain.
Yep,
Oh,
that's good.
okay, I did the minus sign.
So if we have a work day, use that day to take care of this homework, right?
Look at the
She's
calculator.
got a
It doesn't
decimal
like
and fraction.
recognize
I like what I'm
It
saying.
like never
Anything
calculators can't recognize Preston's.
Yeah, okay, I'll take your word for it.
Why not just
Alright.
have both? Like,
Then we talked about complex numbers, adding, subtracting, multiplying, dividing. Hopefully we opened your mind up to a brand new world. Every number that you've been dealing with has really been a complex number, but just the real part of it. There's a whole other world you don't even know about. It's the imaginary part. It's part of a bigger world itself. It's complex. Alright? Okay, it's not quite the Matrix, but it's still kind of fun. Yes.
Basic convert.
That'd be great if it does.
Yeah, they use it.
Okay, good, good. Sorry, I'm
I'm
moving.
starting to sound like my eighth grade science. I'm starting to sound like my eighth grade science. Everyone used the word space, time, continuum, and every. I don't know, like at the beginning of the year, that's literally everyone's.
Y'all literally just exist on this space.
You can solve these problems, you can solve complex homework 1, which is due this Friday.
Oh wow, they just added that. I don't want this juice.
Then just drink it. I don't know.
Okay.
Chug it, Robert.
Huh?
Chug it. Chug it.
If I just ate the box.
I don't know, just
Y'all
give it
drink
a
your
while.
juice with or without the
You did. I need to look and see what you got for the grade ones and things like that. I pulled up the stuff. I saw some things that he had finished. You and I need to look at it though. Somebody. I mean, it was during lunch, so I just made a note that I said, you and I said I'll write Mr.